All right, now we're going to start with part 2. I'll ask that you turn your books to page 517, and we're going to have an exciting conversation about the sea slug, also known as the aplysia. If you look on 517, you can see that Recording2Kandel, who has actually written a lot of neuroscience-type textbooks, has won the Nobel Prize in his studies of the sea slug. Now, why do you think somebody could study a sea slug and win the Nobel Prize? Well, as it turns out, a sea slug is a very simple organism. And if you go back to the field of cognitive neuroscience, if you have a very simple organism, simple in the sense that it only has a few neurons, then what you could do is actually train the organism on some sort of behavioral technique, maybe classical conditioning, operant conditioning, train the organism on this, and then actually see what's going on with the neurons. And that's exactly what Recording2Kandel has done. He's basically taken this very simple animal, and by doing some simple behavioral things and then tracing neuronal pathways with only a few neurons, you can actually unlock some of these key cognitive neuroscience mysteries in terms of figuring out, okay, when there's a behavioral change, what happens in terms of the neuronal structure, the mind-body issue, if you will. And so, I'm going to try to simplify this for you, and I hope it works out. It's been a while since I've done this, but what I would ask you to do is turn to page 518 of your book, and we're going to look a little bit at figure 1411 and 1412. Now, for those of you not familiar with the anatomy of a aplysia, a sea slug, you can look at page or figure 1411. You can see it's got a tail. It's got something called a siphon. It's got a gill that it breathes. There's one motor neuron, and so on and so forth. So hope you're enjoying this education. Figure 1412 is going to be the key one. What I'm going to try to share with you here is what is the phenomenon known as sensitization, which is what I'm going to describe to you. What is it? What happens behaviorally? And then we're going to try to figure out what goes on with the circuitry to allow it. So in sensitization, now think about that word in your own mind, sensitization. If somebody becomes sensitized, you bring up something very simple and easy, and if somebody's real sensitive about the issue, like if I bring up drinking alcohol and you're sensitive about the issue, what happens when I bring that issue up? People get really, really upset. So sensitization in terms of this parameter is the idea of putting a little stimulus in and seeing in a very crazy way that there's a very strong response out. And so what they do for the method in this particular study is they have an organism, a sea slug, and what they'll do in phase 1 is they'll go and touch, if you will, the mantle shelf. And you can see in figure 1412 the mantle shelf, they'll go and touch that very gently, a weak touch to that. Now usually when you touch the mantle shelf gently, the gill will have a very small withdrawal reflex. The gill will withdraw, but in a very minor way, kind of hiding the gill, if you will. The idea is when it's breathing fine, it'll show the gill, but when it feels a little sense of danger, it will withdraw it. So if you touch the mantle shelf very lightly, if you will, a weak touch to it, usually the gill will withdraw, but very slowly and easily and without much of an issue. So phase 1 is just that. You touch the mantle shelf, and they'll have a very slow gill withdrawal response. In phase 2 is kind of interesting. In phase 2, what they'll decide to do is go now not to the mantle shelf, but to the tail. And to the tail, they'll deliver an electric shock. And as it turns out, if you deliver a significant electric shock to the tail, what you'll basically find is there'll be a very rapid and strong gill withdrawal response. There'll be a very rapid gill withdrawal response, which is usually indeed the case. So in phase 2, they'll actually shock this tail to cause the gill withdrawal response, and it'll be a very vigorous gill withdrawal response. And then what's really interesting is what kind of happens in phase 3 of this. In phase 3, soon after phase 2, so once you do this electric shock and such, in phase 3, shortly after phase 2 is over, what you'll basically start to do in phase 3 is you'll go back and you'll start touching the siphon, you'll touch the mantle shelf very gently again. But now, when you touch the mantle shelf very, very lightly, all of a sudden, you now have a major gill withdrawal response. So this is classical conditioning, if you will. So the pairing of the tactile stimulation with the shock stimulation of the tail, so they kind of pair that up, if you will. I may have not said that right previously, but they'll pair this thing up. And then basically what will happen is if you just touch the mantle shelf alone, all of a sudden you get this strong gill withdrawal response. So let me try to summarize this again, because I don't think I did it quite right. The key trial with this is when you actually, in phase 1, you touch the mantle shelf lightly, and then you get a minor gill withdrawal response. In phase 2, you actually do it, I believe, together. You touch the mantle shelf gently, but you do the electric shock as well at the same time, and you get this very strong gill withdrawal response. And then in phase 3, you go back and touch the mantle shelf lightly, but now instead of having a gentle gill withdrawal response, you have a very strong, vigorous response. So hopefully that makes sense to you. Sorry about my slight confusion earlier on. So the question now you know the method and you know the result, but now, well, you kind of know the method. The next step to this project is kind of the interesting one. Once again, if you're in the field of cognitive neuroscience, what would you do with this? Well, you try to figure out what's going on when you're doing this classical conditioning technique of sensitization. Is there a change that's basically allowing a simple touch to the mantle shelf to now lead to a strong, vigorous gill withdrawal response? And the answer appears to be yes. What they've actually done is trace the anatomy of things, and if you look at that picture, you can kind of see it there. Can you see that if you touch the mantle shelf, it stimulates a sensory neuron, and that sensory neuron, it's a little circle there, goes all the way to that little triangle. Do you know what that little triangle is? That is the presynaptic region of the sensory neuron, and it looks like that has a synapse right to the motor neuron, which will cause the gill to withdraw quickly. So, under normal circumstances, in phase 1 of the study, when you just touch the mantle shelf, the sensory neuron gets activated. It'll cause the release of some neurotransmitter on the motor neuron, and then there'll be a slow gill withdrawal response. But what we said happens now is somehow pairing it up with the electrical shock changes everything. And what they've basically been able to find here is that if you pair these two up, that the reason the weak touch in phase 3 causes such a strong response is because of the following. When you pair them up, and if you shock the tail, it seems the tail has a connection with an interneuron. The tail has a connection with an interneuron. Do you kind of see that sensory neuron? And then you see this interneuron. The interneuron gets activated, and do you see where the interneuron has a connection? And I hate to say this, but this is the truth. The facilitating interneuron has a connection to the presynaptic region of the sensory neuron of the mantle shelf. Do you see where that is? I hope you can see it in that picture. It has two little dots there. But basically what happens is when you stimulate these two things together, they've been able to trace down the exact microbiology here, and they find basically that when you stimulate these together, that facilitating interneuron will cause an action potential to happen in that sensory the sensory neuron, and it'll basically keep the action potential going on for a longer period of time. If you read in that paragraph right below there, you can see they've actually traced this down, and they basically find that the sensory neuron will have a much longer action potential because the interneuron blocks, I think they said, blocks potassium. So basically that sensory neuron is going to have a longer action potential, and thus extenuate the action potential and make a minor response into a major response here. I hope this makes sense too. You can read the little details in here a bit longer, but it'll basically extenuate or continue the action potential, so you'll have a major gill withdrawal response. So this is, once again, what people do in the field of cognitive neuroscience. Kandel has won his Nobel Prize by basically showing that you can take a simple procedure here like sensitization and trace it down to exactly what's going on in terms of the neurobiology. There's a change in how the connection works, how the connections lead to this outcome. So this is the sea slug, and hopefully this makes sense to you. Thank you.